Good morning, everybody. This is Indira, Assistant Professor of Institute of Aeronautical Engineering, Department of Mathematics. Already we have started our third module, that is functions of several variables in linear algebra and calculus, one of the maths paper for BTech first year. So in this functions of several variables, in the last session, we have started with Rolle's mean value theorem. Today, we'll see the next mean value theorem, that is Lagrange's mean value theorem. Already we have discussed how to check the continuity and differentiability of the given function in the last classes, in the last session. So today, we'll see the Lagrange's mean value theorem. In order to apply the Lagrange's mean value theorem, the first two cases are common, as we have seen for the Rolle's theorem. That is, first is continuity, second is differentiability. Now, that means we have to check that the function is continuous and the function is differentiable in the open interval. Whenever if these two conditions are satisfied, then we can apply the Lagrange's mean value theorem, just like Rolle's mean value theorem. So let us see the definition of the Lagrange's mean value theorem and try to understand the geometrical interpretation of Lagrange's mean value theorem. Let f of x be a function such that it is continuous in the closed interval a comma b, and secondly, it is differentiable in the open interval a comma b. Then there exists one point C in the open interval a comma b such that f dash of C, the derivative of the given function, is equal to f of b minus f of a by b minus a. Okay, and here the geometrical interpretation, it says that whenever a function is continuous in the given closed interval and differentiable in the given open interval, then there exists one point in between the open interval a comma b such that the derivative of the function is equal to f of b minus f of a by b minus a. That means the derivative of the function is a chord which is parallel to the tangent, which is parallel to the given chord. So let's suppose that f is a function from the closed interval a comma b to r, be a function satisfying the two conditions of the Lagrange's theorem. Then here I have two graphs. Here I have two graphs with me. Here I can show that in the first graph I have a single tangent which is parallel to the chord, given chord, which is touching the 2 points a and b. And in the second graph I can have 1, 2, 3, 4 tangents which are parallel to the given chord. Okay, so this is nothing but the geometrical interpretation of that means the tangent of the curve is parallel to the chord of the given curve. Then that is nothing but the geometrical interpretation of the Lagrange's mean value theorem. You can see that f dash of C, which is equal to f of b minus f of a divided by b minus a. If suppose a and b are equal, then this value becomes 0. Then in that case, the Lagrange's mean value theorem goes to Rolle's mean value theorem. The only difference between the Rolle's mean value theorem and the Lagrange's mean value theorem is that the function, the curve, if they are of same, the end points of the given curve are of the same point, then it is Rolle's mean value theorem. And if they are a distinct point but still the continuity and the differentiability are satisfied, it is Lagrange's mean value theorem. Okay, so y is equal to f of x is continuous in the closed interval a comma b. At every point x is equal to c. When c lies between a and b on the curve y is equal to f of x, there exists unique tangent to the curve. By Lagrange's theorem, there exists at least one point c belongs to the open interval a comma b such that f dash of c is equal to f of b minus f of a divided by b minus a. Geometrically, there exists at least one point on the curve C between A and B such that the tangent is parallel to the chord. But for the Rolle's theorem, the tangent is parallel to the x-axis. That is only the difference between Rolle's theorem and Lagrange's theorem. Because if both the curve and edges are of the same height, definitely the tangent drawn towards a point is parallel to the x-axis. Okay, but for the Lagrange's theorem, it will be parallel to the chord of the given curve. Okay, now let us go with one problem of verifying Lagrange's mean value theorem. As you have seen the two model of questions in the Rolle's mean value theorem, here also we have two model of questions. Of course, three model of questions are there under the Lagrange's mean value theorem. One is verifying, another one is usage, and third one is using, that means finding out the inequality, proving the inequalities by using Lagrange's mean value theorem. So let us go with one question, that is verify Lagrange's mean value theorem for f of x is equal to x cube minus x square minus 5x plus 3 in the closed interval 0, 4. Now, as I have discussed in the previous session, that whenever a function is a polynomial function or exponential function or trigonometrical function with sine or cos, then they are always continuous. There is no need for us to check the continuity because they are always continuous whatever point you substitute. So here f of x, which is equal to x cube minus x square minus 5x plus 3 is always continuous in the given interval 0, 4. Therefore, the first condition of Lagrange's mean value theorem is satisfied. Now going to the second condition. In the second condition, we need to check the differentiability of the given function. The differentiability of the given function. To check the differentiability, we need to find out the derivative of the given function. So f dash of x is equal to 3x square minus 2x minus 5. Okay, and to our view, whenever x, if you take whatever value between the open interval 0, 4, the value, the f dash of x gives a finite value. So you can say that if dash of the x is differentiable for all x belongs to open interval 0, 4. Therefore, the second condition of Lagrange's mean value theorem is satisfied. Okay, so therefore, we are right to apply the Lagrange's mean value theorem. So by Lagrange's mean value theorem, as the function is continuous and differentiable, there exists some c belongs to the open interval 0, 4, such that f dash of c is equal to f of b minus f of a divided by b minus a, and here we will take the b value as 4 and the a value as 0. So let us see what we are going to get. So we have f of 4 minus f of 0 divided by 4 minus 0. So let us calculate what we are going to get this value as. F of 4 is equal to 4 cube minus 4 square minus 5 into 4 plus 3 minus f of 0 is again 3. Okay, divided by 4. These two gets cancelled. 4 cube, that is 64. 64 minus 16 minus 20, which is nothing but the 64 divided by 4. 64 minus 36 divided by 4. So we'll calculate the value of 64 minus 36 divided by 4. That is nothing but some 18 divided by 4. Okay, so that is nothing but we have this point as is equal to f of 4 minus f of 0 divided by 4, that we have already calculated here. So we are going to get this as, we'll try to find out this value and check whether it lies in between the given interval or not. Okay, so f of 4 is equal to that is some value we got it as 64 minus 16, 64 minus 16 minus 20 minus 3, which is equal to 31. F of 0 is nothing but 3. So this value I got it as 7. So therefore from the equation f dash of c is nothing but what? 3c square minus 2c minus 5 is equal to 7. So we'll get the quadratic equation here. Upon solving, c value is nothing but 1 plus or minus root of 37 by 3. Okay, and we'll get two values. Among that, 1 plus root of 37 by 3 lies between the 0 comma 4. Therefore the Lagrange's mean value theorem is verified. Now we'll go for the next question, that is log of x to the base e. Verify the Lagrange's mean value theorem for f of x is equal to log of x to the base e in 1 comma in the closed interval 1 comma e. This function, given this function, what is the function log of x to the base e, is a continuous function. It's always logarithmic functions are always continuous functions. So in the interval, what is in interval 1 comma e? So the first property is satisfied. The second property of Lagrange's theorem, that is the derivative. The derivative of log of x is nothing but 1 by x. The derivative of log of x is nothing but 1 by x, and we can able to take the x value from 1 to e. Between 1 to e, we don't have any point where f dash of x goes to infinity. Therefore, f dash of x is differentiable in this interval. Suppose if you change the interval, then we may not get the differentiability condition. But as the interval is 1 comma e, the condition is satisfied. Okay, so therefore there exists a c in the open interval 1 comma e such that f dash of c which is equal to f of b. F of b means f of e minus f of a. A is nothing but 1 minus f of 1 by e minus 1, which is equal to 1 minus 0 by e minus 1, 1 by e minus 1. E is nothing but 2.713. So 1 by 2.713 minus 1, which is nothing but we can get the value as c is nothing but e minus 1, 2.713 minus 1, which is nothing but 1.713, and which always lies between 1 and 2.713. So that is how we can verify our Lagrange's mean value theorem for the second example, that is log of x, when f of x is equal to log of x in the interval 1 comma in the closed interval 1 comma e. Okay, so now the third, we'll try to create an example for the Lagrange's mean value theorem. Give an example of a function that is continuous on minus 1 to 1, and for which the mean value theorem does not hold, and we have to explain it also. Now for this, I will take the function f of x is equal to mod x. Mod x, we all know that it is continuous function, because mod value between minus 1 to 1, it is always continuous. Even if it is 0 also, it is a finite value. So therefore mod of x is a finite. But if you go for the differentiability, we have to check the left hand limit and the right hand limit. Both we have to check here, right? So if you go for the left hand limit of x tends to, that is 1 minus, right? Okay, f of x we need to check, and the right hand limit we need to check the limit of x tends to 1 plus f of x. Okay, so the other way for showing the differentiability is for the mod functions especially, we need to check the left hand limit and the right hand limit. So here f of x is nothing but mod x. So when x is x 1 minus, so we are going to get as f of x tends to f of x tends to x. That means here we need to calculate f of 0. I have already calculated, right? F of x minus f 0. I mean f of 0 divided by x minus 0. And here also we need to calculate f of 0 minus 0 divided by x minus 0. Suppose if you are taking 0 plus and 0 minus. So 0 minus and 0 plus. So here we are going to get this value as this the first value as mod of x divided by x, and here also mod of x divided by x, but here it is plus 0 plus, and here it is 0 minus. So instead of limit 1, I am checking the derivative as 0 plus and 0 minus. So it's 0 minus, this becomes minus x by x, and this becomes x by x. So both will get cancelled, giving 1. Here also it get cancelled, leaving minus 1. So you can see that the left hand limit is minus 1 and the right hand limit is plus 1. So therefore the two the left hand limit and right hand limit both are not equal to each other. Therefore the function is not differentiable. Therefore it's a good example for the function which is continuous but not differentiable function. Okay, so like this you can able to explain the differentiability and the continuity of the given function, which is helpful to find out the the derivative of the given function, and to find out the solution of the given function, and to find whether the function is increasing or decreasing using mean value theorems. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.